Hi there. Today we're looking at meta-learning with implicit gradients by Arvind Rajeshwaran, Chelsea Finn, Sham Kakad, and Sergey Levine. So this paper deals with the task of meta-learning. Now, if you don't know what meta-learning is, let me quickly introduce the term. So in meta-learning, you assume you have some sort of a distribution of tasks ahead. So let's make some examples. For example, task 1 could be you get an image, you have a data set of images, right? And you want to classify them into cats or dogs. And you have a little data set with labeled images, and you can train, test, split that, and that's one task. Now task 2 is going to be, again, you have a small data set of different images, but let's just all make image examples here. But you want to locate the pedestrian. So you want to locate the human in the image. So where is the human? Right. And the task 3 could be, again, a small database of tasks, of images. And in each of the image, you want to visually question answer. You want to, or let's say, you want to point out, all right, there is a ground, there is a tree, and there is a question about it. Yeah, let's say visual question answering, right? Which give you yes or no questions, something like this. Now let's just say you have to segment. You have to segment that image. So down here would be ground. You have to segment the ground. Okay, so these are all image tasks, right? These are all perfectly fine independent tasks. For each one you have a small data set. Now, sometimes these data sets are very, very small, such that you cannot really train a state-of-the-art model on them. For example, if you have medical images, oftentimes the labels of these are very hard to get. I mean, there's privacy concerns, and then doctors have to look at it. To produce the images costs money and so on. So it's not like you have a lot of images, and you could profit from more images. So one method that people come up with is called transfer learning. So in transfer learning, you say, I have this giant database of images. Let's say this is ImageNet, right? I have this giant database, ImageNet, with labeled images. What I can do is I can use this to train a neural network. These are the bunch of layers of neural network, and I can train the neural network on this big database and get parameters theta, right? These are the parameters of the neural network. And then I will basically adapt these parameters to each task individually. So in task 1, sorry about that, I would then take these parameters as an input to the neural network. I would initialize the neural network with these parameters, and then I would use this training set in order to fine-tune. This is what's called fine-tuning to the task-specific parameters here, phi. So phi 1, because it's task 1. For task 2, I would also take these as a starting point in order to train its neural network to fine-tune it on this bounding box task in order to obtain the parameters for task 2, right? So you can see that there's the pre-training stage here to obtain good initial parameters, and then we adapt these initial parameters for each task separately in a fine-tuning stage. So this is one way we can do it. Another way we can do it is called multitask learning. What we do in multitask learning is we say, well, see, probably a neural network that can segment the ground is also pretty good at doing bounding boxes. Like, it will use some of the same features. So can't we just kind of pool together these data sets into one bigger data set and then train on, like, if it's an image from task 1, we'll train on the loss of task 1. And if it's an image from task 2, we'll train on the loss of task 2, and so on. But we'll sort of use the same neural network basis. We just have kind of different heads on top of them. And we'll basically, so this is called multitask learning. Have one shared neural network with different outputs for the different tasks. And basically counting on the fact that you can sort of learn from one task what's useful in the other. Now this is a good method to combine the tasks and to basically share data information, but it will also limit you because you now have to trade off between the tasks. Like this neural network right here, this joint encoder, will never be able to fully gear to one task because it also has to, it has to perform for the other tasks as well. So you kind of limit yourself in your top-out accuracy. Now maybe the regularization effect is good. So these are two methods. The first is called transfer learning here on the left, and the other is called multitask learning. Now, meta-learning goes a different direction. Meta-learning is like transfer learning, but it says, well, what if we don't have this giant data set right here? What if we find a way to learn these initial parameters, right? So what we'll do is we'll start out with a guess of good initial parameters. Let's call that theta 0. And now we have all of these three tasks take theta 0 and run their fine tuning, right? To come up with their own parameters starting at theta 0. So this is phi 1 started from theta 0, and we'll also give it to task 2 and to task 3, right? And each of these tasks is going to train on its own training data set and then evaluate on its own validation data set and then report back a number. So we do this for every task, and every task basically trains this, runs through the validation data set, reports back a generalization error, and then we know, once we get all the information from all the tasks, we know how good were these initial parameters, right? We get a measure of how easy is it for the tasks to adapt these initial parameters to their own data set. And then we somehow need to figure out a way, okay, these parameters were on average 81% good. Can we come up with a better set of initial parameters, theta 1? In some way, can we somehow find a better set of initial parameters such that it is easier for the tasks to adapt these initial parameters, right? And even more so, there could be task 4, which we are not seeing during this training phase, right? This is kind of so these up here could be our training tasks, and this down here could be our validation task. So basically we're trying to come up with a set of initial parameters that if a new task comes along and it takes this thing as its initial parameters, it will be able to adapt very quickly these initial parameters to its own data set. And most importantly, it can do that. It will result in a much better model than had the task just trained on its own small data set from scratch. So our task in meta-learning is basically to come up with a learning procedure to iteratively generate better and better and better initial parameters, right? And what better way to do this than using gradient descent? So this is meta-learning using gradient descent is the core of this paper basically. Now, what do you need for gradient descent? So if you want to go from one task to the next using SGD or even GD, gradient descent, you need to come up with a gradient. Now, why is this a problem in this case? So this is in this figure. So this meta-learning using gradients was done in this technique called MAML. And essentially, what you can see here is that if you have this set of initial parameters, this is your current best guess of these good initial parameters, and you want to come up with a gradient of how to get an even better set. Now, this gradient here is indicated by this arrow. So let's imagine you don't know the gradient yet, you want to come up with a gradient. So what you'll need to do is you'll basically have to compute the loss function, and you have to differentiate that loss function with respect to your parameters. That's down here, what the description of the orange arrow. So your loss function of your meta parameters is going to be the average or the sum of the loss functions across all of the different tasks individually. So the gradient is going to be the sum of the gradients of these loss functions with respect to your original parameter. Now this is the difference, right? Usually we differentiate with respect to the parameters that we input into the loss function, but not here. What we input into the loss function is what is at the end of the task adapting to its own parameters. So this thing we input here is a function of our initial parameters, but is not our initial parameters. So what we have is initial parameters. We give them to a task. This task runs SGD for k steps. It runs it for a number of steps, comes up with the adapted version to its own problem. That goes into a loss function, right? So this thing here is the neural network that finally determines the loss function. So if we want to backpropagate, we can backpropagate this loss function, right, through the neural network. The neural network is right here, is parameterized by these things. We can backpropagate through that, but then we'll have to backpropagate through the optimization procedure that was used to derive these things. So that's the problem right here. You can see this here. You start out with the initial parameters, and let's say you give them to task 1. Task 1 is going to take these as initialization and then run SGD. So maybe it will perturb these parameters to come up with here phi1. These parameters are the adapted version for task 1. And then at the end of task 1, you use these characterize a neural network and you can calculate a gradient. So how would you need to update these parameters in order to make the loss go down? And the neural network, the computation will maybe result, well, you need to go up a bit. Well, this is too strong. It will maybe say you need to go into this direction right here with respect to these parameters. But now the question is, how do you have to adjust your initial parameters such that your final parameters will go into that direction? And that's not really clear. You could make a guess, right? You could make a guess and say, well, if my initial parameters just go up a bit, maybe the optimization procedure will just, sort of look the same, but shift it up here. So something like this. And then I will end up here. But that's not guaranteed. Like, this is a super nonlinear procedure that you're running it through, this SGD thing, and it will basically, it's an iterative recursive procedure, so it will sort of accumulate its own nonlinear errors, and that's why what you have to do is basically you forward propagate through SGD, and then you have to backpropagate this gradient right here. You have to backpropagate this through the entire SGD optimization procedure. And that is computationally very expensive, because if you have to compute the loss once here for a neural network, you have to forward pass once, and the backpropagation will cost as much as the forward propagation, or maybe twice as much, a constant number. But if you run k steps of SGD, you basically have to trace back those k steps via backpropagating it through each step. So basically this is k times a backpropagation step. And computationally, that's just not feasible for more than very few steps. And so you can only ever do very few steps. You basically accumulate your nonlinear error, because gradient descent is a linear procedure. And then you get some estimation of the gradient at the end. Now, if you do that for all of your tasks, then finally you can decide. So maybe for task 1 here, the result will be, in order to make this go up a bit, you need to shift this a bit to up and the right, because then the gradient descent will kind of sort of end up here. And you do this for all tasks, and you average the gradient like here. Then you can come up with a final gradient for your outer model, for your initial parameters. So this is a big load of computation that MAML does here. Now there is a naive approximation, and this is exactly what we said at the beginning, right? This first order MAML is the guess that if we want to go up a bit at the end here, why don't we shift the beginning up a bit, right? And so the first order MAML would just result in basically looking at the gradients at the end and sort of aggregating them right here and then coming up with a gradient. But this is very inaccurate and generally doesn't work well because you have to understand how your end gradient is connected to your initial gradient. Because this is very nonlinear, you can't just basically transfer it over. Now, implicit MAML, this paper right here, circumvents that. It circumvents the step to have to explicitly backpropagate this gradient along the forward pass, but it's still able to come up with an expression for how the final gradient relates to the initial gradient. So this is quite cool, and in this video I would basically like to explore how this comes about and why this comes about. We won't go through all the theory and the proofs, but I would like you to understand that this comes about by basically them imposing a quadratic regularizer, and therefore this quadratic regularizer makes it kind of gives rise to a very strong connection between this final gradient and this initial gradient. So they can basically transform one into the other, and therefore they can compute the initial gradient in a closed form setting, or at least in theory. All right, this was this. Now let's go into the problem formulation as they see it. The entire problem formulation is you want to find these best meta-learning parameters, right? And they call this the outer level. So on an outer level, you want to run gradient descent to find the best meta-learning parameters to minimize this function f right here. Now, what is f? F is the average of the validation loss function. So here, this is the loss function on the test sets of the individual tasks. And the neural network that we evaluate on the test set is the neural network that is trained. The alg here is a training algorithm, is trained on the training set of that particular task while starting from these parameters theta. Now you see there is no dependence on the task here. There is no I down here for these meta parameters because these are always the same, right? That's the crucial point. All the tasks start from the same initial parameters, then they optimize on their own training data set, and then they evaluate on their own test data set, and that will give you the loss for that particular task. And your goal is to find the meta parameters such that this function here, the average loss that results from this procedure, is minimal. Okay, so where they say right here, the inner level is this algorithm component. So the algorithm starts from these meta parameters and runs gradient steps on the training data set loss. Now this is just the first step right here of this procedure. Of course, in the next step, these are going to be replaced by the phi I that results from the previous step. So the first step is run on the meta parameters, and then subsequently the task-specific parameters are updated. The important thing here is that this doesn't need to be gradient descent actually with their method, because their method doesn't need to backpropagate through the optimization. You can think of any inner optimization procedure that you want. It can be like a black box solver, whatever you want. I'm going to be interesting to see how this is going to affect something like reinforcement learning and so on. This might have already happened, and I have not looked up this. So the crucial part of the paper, I think, is right here, and it's sort of like, section 2.2. But I would want to point out that I think this is the crucial part. This is why the method works ultimately, why it's able to build this implicit gradient. So the section is called Proximal Regularization in the inner level. And we'll go through this with a bit of detail. To have sufficient learning in the inner level while also avoiding overfitting, ALG, that's the inner optimization procedure, needs to incorporate some form of regularization, right? So they're So their goal here, or their point here, is that especially if these individual tasks have small training data set, you need to have some kind of protection against overfitting. And they say, since MAML uses a small number of gradient steps, this corresponds to early stopping and can be interpreted as a form of regularization and Bayesian prior. So MAML is this previous method, this basic method that backpropagates through the optimization procedure. And since it does this, since it backpropagates through the optimization procedure, it's computationally limited to only run very few forward optimization steps, because it then has to backpropagate through each one, right? It needs to store each one. So it's computationally limited. So by necessity, it uses only a small number of gradient steps. And therefore, this is kind of early stopping. And we know to prevent overfitting, one thing you can do is to stop before your training accuracy reaches full zero. And you can stop earlier than that, ideally at a point when your validation accuracy reaches the low point. But they say basically this limited number of steps is a form of regularization. Now, of course, in this new method, we don't have this constraint anymore. We can run our inner optimization to super convergence, and therefore we don't have this implicit regularizer anymore, and we'll have to make up for that. They say, in cases like ill-conditioned optimization landscapes and medium-shot learning, we may want to take many gradient steps, which poses two challenges for MAML. First, we need to store and differentiate through the long optimization path of ALG, which imposes a considerable computation and memory burden, right? That's what we said. Second, the dependence of the model parameters phi I on the meta parameters shrinks and vanishes as the number of gradient steps in ALG grows, making meta learning difficult. So what they're saying is, if you optimize your inner optimization algorithm to the very end, then it is not its dependence, and especially for gradient descent, its linear dependence on the initial parameters, so on the meta parameters, shrinks the more optimization steps you do, because the more and more you're going to basically forget about your initialization, move away from that and move to a local optimum, from which you could reach, from many different initializations. So that's still a question of whether that's happening, but that's the idea here, right? If you're at the local optimum, you could have reached that from any sort of point, and there's going to be very little information about the end of the procedure from the beginning, and therefore, if you want to calculate the gradient, that's going to be like super inaccurate. And they say, to overcome these limitations, so they solve these two things in one right here. We consider a more explicitly regularized algorithm. So what they'll say is, we don't just want to optimize this inner objective. So this would be here. So we don't just want to find the minimum of this inner loss function. That's one goal we have. But the other goal we have is to stay close to the initial parameters. And that's where this regularizer comes in here. So this basically says, we want, with our parameters here that we are optimizing, we want to find them such that they minimize this loss function, right? Really minimize it, find the best point. But also, with a trade-off of lambda, we want to stay close to the initial parameters that we started from, right? This is the initial parameters, and the closeness is measured in the L2 norm. So it's a quadratic regularizer on how close you are. You might know from initial supervised learning or something that sometimes you do something like plus lambda times the L2 norm of the weights. So this would be called weight regularization, weight decay, L2 normalization, something like this, where you regularize your weights such that you stay close to the 0 point, right? Implicitly in this, there is a -0 given. But here, you want to stay close to your initial parameters. So the inner optimization is no longer just minimizing the loss on the training data set. The inner optimization is that. And with alg star, we denote, so if alg has a star, we say that this is referring not to the procedure of the algorithm, but to the minimum that the algorithm has found, right? So alg star means the algorithm has optimized this inner procedure to its minimum, which is a balance of the training loss of that task and staying close to the original parameters. And this, I think, this, they say that here, the proximal regularization term in equation 3 encourages phi I to remain close to theta, thereby retaining a strong dependence throughout. This is why their method works. And we're going to see in the math right soon how exactly how exactly they're able through this to establish this implicit gradient correspondence. So they formulate their entire algorithm as follows. We want to find the best meta-learning parameters by minimizing the function f, where f is the average losses, and L here, now that's the test set loss, the average validation loss for each task of the parameters that the inner optimization procedure finds when it runs to its optimum. Now this, you can see here, this is already different from the original MAML. The original MAML was simply running it for a number of steps, and now we're really running it to the optimum, at least in the ideal case. What does the inner optimization algorithm do? The alg star here minimizes this function g. Right now, g has two arguments. G has these parameters, which are the local parameters, and these are the meta parameters. And we only optimize the local parameters. Right? We take these as initial and then fine-tune them. Where the function g is defined as the training loss of the local parameters plus this closeness regularizer. Okay? Cool. Now the question, of course, is how does that lead to gradient descent? So ultimately, we want to minimize this function f right here. So we're going to have to do something like df by d theta, right? In order to run gradient descent, we need to calculate this gradient because we need to do gradient descent. So what's that going to be? That's going to be, of course, since f is this 1 over m up here, right? The gradient simply distributes over that sum. Now it's the gradient, or sorry, the derivative of each of these inner loss functions. Let's go with this alg star I theta. That's basically what you have right here. Okay, so in order to take the gradient of f, we need to be able to take we need to be able to derive these loss functions, and you can see right here, theta is not the argument to the loss function, theta is the argument to this inner procedure. So by the chain rule, right now this gives us this. So the chain rule says we derive the outer thing with respect to its input. That's this part right here. The gradient of the loss with respect to the neural network, and that thing here, that's the alg star, right? So we need the gradient of the loss function with respect to the end parameters of the optimization procedure. Now that's easy. We know how to do that. So if you remember the drawing at the beginning, this gradient is the end arrow right here. This is easy. This is one backward propagation. This is regular supervised learning backprop, right? You have parameters of a neural network, a gradient for the loss function. Cool. The hard part is to have the derivative of the algorithm itself with respect to the meta parameters. Right? So this here is going to be a vector. It's the gradient with respect to these parameters, and this is going to be a matrix, and the matrix will relate basically one dimension. Each dimension of this vector, this is going to be a product between this thing, and it will result in this thing. So the left thing is the gradient we want. This is the derivative of the entire thing. That's this. Now the right thing is the gradient at the end of the optimization procedure. And this matrix here relates the individual dimension of this end gradient to the gradient that we want, right? This is a matrix that relates the two in a linear fashion. This is what we're looking. How do we need to change the initial parameters in order to change the end parameters by in a certain way? Because we only know this, but we want to know this. So how do we calculate this thing here, this Jacobian? That's the question, right? How do we derive the algorithmic procedure, this thing here? And the paper goes on to say, well, okay, yeah, so we need to do this. This is the entire gradient descent optimization procedure. So we must compute this thing right here. And they just throw it in your face. It's this, boom, shagadabam, this thing here. Done. Let's go on. No. So you can see it's basically putting this just right here, but we kind of want to explore where that comes from. So the fact you can see here, you can derive this gradient as a closed form expression of the inverse of a matrix that contains, this is the identity matrix, contains somehow this lambda factor that we saw before, and it contains this Hessian matrix of the training loss, right? So this is this end gradient that we can calculate easily. And the second derivative of that is the Hessian, which is basically the curvature in the landscape of that loss. But nowhere in this thing is the SGD procedure showing up, even though this thing here is the SGD procedure. And that's pretty impressive, and we're going to look at how that comes about. So where do we start? First, let's take this g right here, this g function, right? And let's calculate the derivative with respect to these parameters right here. So let's go for this end gradient. What's this end gradient going to be? So we'll derive the g with respect to these parameters. All right. So this is a sum. This first thing is pretty easy. It's going to be the gradient of this loss function. Loss function is a scalar, right? So we can calc. This is simply one backward prop through the network. The second thing we can also do pretty easily. This is an L2 norm, all right? We know how to derive a square. So the 2 comes down, and this will simply result in this vector right here. So it's going to be lambda times phi minus theta. Okay, now this was relatively easy. Now, imagine what happens when in this particular thing we have one additional information, namely that f, the inside of f, we will always optimize to the end. We will always optimize this to its minimum, right? This star denotes that the inner optimization procedure will always go to the minimum of that function. So what do we know about the minimum of a function? We know that its gradient at that particular point is 0. Right, this is an important part. So now we can restructure. So if we take one to the right, I might actually use black here because it's kind of burning my eyes. We can isolate this part right here. So we say the phi is equal to, first of all, let's take this to the right side. So we'll have this gradient right here, and I'm just going to write L phi. Oh, let's keep the hat alive. We'd have to divide this by lambda, right? And then bring over the theta. So we have an expression that says at the optimum, the parameters phi, the inner parameters, are going to be given by this expression. Now that's pretty cool. But we know also that these parameters aren't just, parameters per se. They depend on these parameters, right? The end parameters depend on the initial parameters because we use the initial parameters to initialize these end parameters. So these are actually a function of the initial parameters. So what we can do is we can derive this, using red again. Let's use blue. We can derive this thing by the initial parameters, right? How do the end parameters relate to the initial parameters? Now, this is our basic question all along, but we now have an exact expression for the end parameters, which we didn't have before. Before, we just knew they came about by SGD. So, important to say this only works at the optimum, right? This is at the optimum that this relation counts, not anywhere. And the paper is abusing this quite a bit right here. So what does this do? If we derive this thing here with respect to theta, it's simply giving us the identity matrix, right? This is now our Jacobian that appears here. It's simply giving us this. Then this 1 divided by lambda is going to stay. And now it gets a bit tricky because these things right here, of course, are also a function of theta. So essentially this means this thing right here is a gradient of a function of another function of theta. So we can apply the chain rule again. Since this is already the first derivative, it will give us the second derivative with respect to the loss function right here with whatever goes into the loss function, so that times the inner derivative. Now the inner derivative is simply how to derive again the phi by the theta. Okay, now okay. Yes, so you can see, first of all, interesting that the expression here, or the expression that we're looking to find, appears in the expression itself, right? Since these parameters appear over here as a function argument as well, we'll get basically this expression here twice. But we can reformulate that and find that this term, this Jacobian, is basically this here inverted. So the matrix we're looking for is, the inverse Jacobian. The matrix we're looking for is given by this quantity right here, the identity matrix minus this Hessian term right here. Okay, and this is exactly what you see appearing here. This is exactly that. So the derivative we're looking for, this is actually the Jacobian, not the inverse. That's my bad. What you're looking for is given by this expression. Now my eraser got stuck. Hello. Cool. So that's how that appears. You see, it's the same thing if I had done everything correctly. So this you do by simply shipping this to the other side, which will make it the inverse, right? So you basically divide both sides by this, and then you get this as an inverse. Now, why does this work? Again, I want to stress, why did we get this identity here? Why were we able to express, get a closed form solution to for the inner thing? Or sorry, for the end parameters in terms of the beginning parameters that doesn't have SGD. First reason, because we optimized to the end, to the optimum. That's why we got the equals 0 right here. Second reason, because we have this regularizer. You see this directly comes from this expression right here. If we wouldn't have this regularizer, then we could not make this expression. We could not get phi as a standalone quantity here, and therefore this derivation wouldn't work. Now, why is this important? Because if you look back into your drawing, what you're basically doing is you are imposing a quadratic regularizer around this initial point right here. And that creates this very strong connection between the end gradient and the initial gradient. So now when you're optimizing, when you have a training loss of the inner task, and maybe the training loss looks something like, like this right here. So SGD would go right to the very inner point right here. If you just let SGD run, it would go there. But now, since you have this regularizer, SGD needs to find a trade-off point between the two. So what it will do is it will probably go somewhere and stop somewhere here. So it will now have two forces pulling on it. The first force will be this quantity right here, and the second force will be pulling it back towards this. And you can pretty much count. So now SGD cannot just go to any point right here. It cannot not go to any isoline. These are not equal anymore. Mainly it will go to the one point that points into the direction of this quadratic right here. So since it's a quadratic, we have closed form formulas for relating one gradient on the quadratic, namely the one out here, with the gradient back here. So we can express this Jacobian in closed form because this is a quadratic, because we have this regularizer, because you have these basically two forces pulling on this point in opposite direction, one pointing towards the training loss and one pointing towards the inside of the quadratic. So that's why this method works. Okay. I can recommend Ferin Huzar's blog post. He has some very nice animations of why this basically restricts where gradient descent can go. I can link to it in the description. It's pretty cool to see. I don't have it open right now. So, what does that give us? The implicit model agnostic meta learning, iMAML. This is what this paper suggests. While not converged, do sample a bunch of tasks, right? For each task, compute the meta gradient G, average these gradients to get a gradient for the outer parameters, and then do gradient descent on the outer parameters. Pretty easy. How do you do this? How do you do this implicit meta gradient? This is this procedure right here. So what you are going to do is meta parameters theta, you initialize your parameters with the theta. By the way, they don't need to be initializations. They can be actually any sort of hyperparameters that this algorithm takes. Any parameterization of this algorithm will do fine. I just always said initial parameters such that it gets easier. But it can be any sort of hyperparameters of the inner task. Obtain task parameters using iterative optimization solver such that the the inner parameters are close to the optimum of that algorithm. So they actually extend this also in theory, not so that you don't have to optimize the inner objective really to the optimum, but you can be like a delta close to it. That's pretty useful. And that's in the part of the paper that we won't go over because this video would be like super long, but I invite you to read it if you're interested. Then you compute the partial outer level gradient. So this would be your partial gradient, your V would be this gradient at the end, right? The gradient at the end of the optimization procedure with respect to your validation data sets. This is one backprop. Now we need to relate that end gradient to the beginning, and we do that by multiplying it with this matrix inverted right here. Now, because obtaining the entire matrix, this is the Hessian matrix, and invert it is very memory and computation intensive, because if you have D parameters in your neural network, this is going to be a D by D matrix. So if you have 5 million parameters, this is going to be 25 million size matrix. Is just not possible. And that's why this paper extends this method to a second degree of approximation, namely, you don't have to compute the exact inverse, you just have to compute something that is very close to the inverse times this this final gradient. And a good method to do this is this conjugate gradient method, and that method is able to basically use the fact that you can compute Hessian vector products without having to compute the Hessian as a matrix. This you can also do with a sort of modified backpropagation algorithm. Also won't go in here, but so you use iterative solver, for example, conjugate gradient, along with reverse mode differentiation to compute Hessian vector products, to compute GI. So GI is going to be the final gradient pulled back through this matrix right here to give you the beginning gradient, this meta gradient. Okay, so two approximations here. First approximation, you don't actually have to solve to the very end. You can solve it delta close. And second approximation, you don't actually have to compute the inverse of that final gradient, compute the multiplication of the final gradient with the inverse of this matrix right here. You can also find something that's a delta prime close to that. And they have a bunch of theory of that this still works. They compare this, of course, to the other algorithms. They observe that their algorithm uses substantially less memory and substantially less less compute time once you go up to a number of inner gradient steps. And it works better than this first order MAML. So this first order MAML was our kind of initial guess of how we could do this. This tends to perform very poorly. As you can see, you can't actually see that here, that their method is better, but their method is better and uses less time because you have this inner conjugate gradient optimizer. Sorry, this is the outer optimizer. Okay, so this is the error plot of how well are these methods able to approximate the true gradient. So if you could compute this true outer gradient, that we did with MAML, but we optimized to the end, how close are you getting? Of course, the problem with this method right here is that you do these approximations and those could hurt you. But the problem with MAML is that you're backpropagating through the optimization procedure, and that means the nonlinear errors could sort of accumulate. And as you can see here, even though both might eventually, get to the zero error if you give them enough inner gradient steps, especially at the low inner gradient step regime, the implicit MAML is much better than MAML. Now, I've just said the errors accumulate, but the effect probably here is that the fact that with MAML, you don't actually do good enough inner steps to reach a good enough optimum of the inner tasks. So these inner gradient of the tasks, they're gradients when they're still very not optimized, and therefore they are a very bad estimate for your outer gradient than when you do more gradient steps. So that actually hurts you more, which is also a bit surprising to me. And then at the end you see these conjugate gradient steps. This is when you approximate this matrix inverse. If you just do 2 steps, then at some point that error dominates. But if you do more steps, you can reach a much lower error. And 10 steps isn't that much for an algorithm like this. As you can see here, the 10 steps, your computation time will still, in the regime of many gradient steps, will still be lower than the original MAML. And then they actually test this thing, and of course they're the best at pretty much everything. I don't want to go into the exact details here. I invite you to check out the paper for that. Check out if you're interested in the proofs and the approximation guarantees. And with that, bye-bye.